complex variables. I'm Matt Garcia. You can call me whatever you want. I don't care. I prefer you just call me Matt. That's fine with me. But if you're more comfortable saying something more formal, that's fine. Whatever you like. Right. So just a couple logistical things before we start doing mathematics. I'll have office hours 9 to 10:30 a.m. on Tuesdays and Fridays. In what's my office? Right, 540A, Nightingale. Okay, everyone here's lucky because my office wasn't assigned till yesterday, so it's been ambiguous on I've set my office hours, but you all know. I'll also have simultaneously a Zoom link for my office hours, which will appear on Canvas. Okay, so let me just make a remark about the grading. We'll have the homework will account for 30% of your grade at the end. We'll have one midterm exam, which will also account for 30% of your grade. And the final will account for 40% of your grade. Right, so the date of the midterm is yet to be determined. Since there's only one, it'll be approximately in the middle of the term. Of course, that is a bit of a misnomer when there's more than one midterm, but for us, it'll be in the middle of the term. As for homeworks, I'm anticipating between 7 and 9 homework assignments. And we'll drop the lowest score. Okay. So I just want to take this opportunity to mention that the homework is going to be designed to be very challenging and take a significant amount of time and effort to complete. By contrast, the exams, the midterm and the final, will be comparatively quite easy. Okay, so my point is that, well, there's a couple points here. In doing the homework, when you have difficulties, when you start to struggle, don't panic that the exams will be as difficult. Homework is designed to take time to complete and process. What was the other point? Oh, right, start the homework early, because it will take some time to do, typically. Or maybe I'm underestimating you all. Maybe it won't take that much time, but it's supposed to take some time. Okay. Right. So I'll also ask that you, if you haven't yet, please go to the Canvas page and read the syllabus. There's a lot more logistical technicalities there that I don't feel it's necessary to mention, but I should say that you should read the syllabus. And also, check Canvas very often, right? This is where assignments will appear, announcements, changes to dates of things, due dates, etc. This is where all the information will be collected. I'll do my best, of course, to remind you of these things in person, but just to be safe, check Canvas as often as you can. Right. So, on the subject of turning in assignments, we're fully in person, and in fact, I quite prefer to have physical papers that you turn in because I feel like I can give you better feedback that way. I can write comments directly on your papers, and there's a modality for that in Canvas, but in my experience, people just don't read the comments that I make when I grade their work on Canvas. I have very often had it happen where students come to me and they're like, why did I get points off on this? It's like, well, this, and this, which were actually in the comments on the side. Did you read those? And they're like, oh no, I didn't even see. So, any way you want to do it is fine. If you want to submit your work digitally via Canvas, that's okay. I would prefer that you gave me a piece of paper to grade, but it's ultimately your choice. Okay? Okay. So, any logistical questions before we start? Yes?
Will the homeworks be assigned in class and due in class?
Yes. So, assigned in class, they'll be assigned via Canvas.
Okay.
And then the due date will be at the beginning of some class period that we have. Okay. Yeah. Good. Any other logistical questions? Okay. If anything comes up, my email is questions. Email me. At Northeastern. Yeah, if anything comes up. Oh, I should also mention, if you can't make these office hours, I'm happy to make an appointment at your convenience. So just let me know if this doesn't work for you. Okay, so all that being said, let's begin to talk about complex numbers, right? Our goal is to essentially rederive the results of calculus, integration and differentiation, in the setting of using complex numbers, okay? And some things can be accomplished quite simply, as we'll see in the beginning of the term. But some things which were relatively easy to accomplish for real variables become quite a bit more difficult to establish, but the payoff is worth it, by which I mean we're able to address a much broader class of problems when we consider a complex variable rather than real. Okay, so we'll have to do some work, but in the end, we'll see that it's worth it, or I hope I can convince you by the end of the term that it's worth it. So in order to do this, we first have to lay our foundation. We have to discuss what complex numbers are, what properties they have, and I think it's kind of important to discuss where they come from. Okay, so where do complex numbers come from? And it's to say, what is the historical motivation for complex numbers? Well, that's really quite a manifold answer. There are many streams which converged to the development of complex numbers. But I think something that's one of the oldest ones and a little more down to earth. Let's first start talking about rational numbers. Okay? So, first of all, let's take A and B rational numbers. Okay, and this is a small class, so I'm going to be very explicit and ask you all if you're familiar with the notation that I freely use. Is everybody okay with this epsilon? Meaning that it's an element of, right? Blackboard bold Q with a line is just the set of all rational numbers. Yeah. Okay, good. So let's take A and B rational numbers. Then, the linear equation AX plus B is equal to 0 necessarily has a solution in rational numbers. Namely, well, we just use arithmetic to solve for x here, right? We get x is equal to negative b divided by a. Of course, we must insist when a is not equal to 0. Okay, so any linear equation with rational coefficients can be solved just using rational numbers. Right? We've explicitly demonstrated that by arithmetic. The ratio of rational numbers, which it must again be a rational number. Okay, well, if we continue in this tack, we might ask, how about quadratic equations? Which quadratic equations with rational coefficients can be solved using only rational numbers? And we find relatively quickly that there are many quadratic equations with rational coefficients which do not have solutions in the rational numbers, right? So, let's say, moving up to quadratic equations with coefficients in Q. We quickly find this is not true in general. E.g., let's consider the quadratic equation x squared minus 2 is equal to 0. Okay? I'm making a bit of a claim here. I'm saying that there's no way to express the square root of 2 as a rational number. Just a quick poll. Have we seen a proof of this before? Yes, okay. Good. If we hadn't, I would have assigned that for homework. But now we'll just take it for granted, since everybody nodded. Okay? So that is to say, square root of 2 is not wanted to augment the rational numbers, that is to say, add something in, so that we were able to solve this equation in this new system of numbers, we might well throw in this symbol, root 2. Okay? That is to say, we're doing a formal thing. We're not constructing a new rational number, we're just adding in some symbol which we acknowledge is not a rational number. Okay? So let's formally add in the symbol root 2 to the rational numbers. Okay? And what do I mean by this? So then, and we'll consider numbers, whatever that means, of the form a plus b times square root of 2. Okay? Where, of course, we insist that a and b be rational. Okay. So, at this point, with this new notion of number, we can check that with the appropriate definitions, addition, multiplication, and division possess all the same nice properties that they have in the rational numbers. That is to say, addition and multiplication are commutative. Likewise for division, when you have a non-zero divisor. So let's just write down what the definitions of addition, multiplication, and division should be. And then you can check for yourself that they possess all these nice properties: distributivity, associativity, etc. You can convince yourself of that to whatever formality you like. Okay? So that's fine. One, addition, so we'll take two of these numbers, a plus b root 2 and c plus d root 2, and add them together. Well, we just treat these as we add like components, right? That is to say, we add the parts that don't have a root 2 factor, and we add the parts together that do have a root 2 factor. Right, so this is defined as a plus c plus b plus d times root 2. Yeah. Similarly, take two such numbers, a plus b root 2 and c plus d root 2. And here, we'll just use the familiar algorithm of multiplying binomials. And then when we're done, collect terms which do not contain a factor of root 2. And collect terms which do contain a factor of root 2. Okay, so what does this resolve in? We get a times c. Well, let me just, I think we all know how to multiply binomials, so I'll just tell you the answer. Here are the two factors that result from this multiplication that don't have a factor of root 2. And here are the two factors that do have a factor of root 2. AD plus BC root 2. So at this point, you might be noticing the pattern here. We're kind of just using the standard way of computing with rational numbers. We're just computing around this root 2. It's this kind of like inert thing. So yeah, this is kind of what I mean. I didn't say exactly what formally means, but we're treating this like just a symbol that we can manipulate in a way, even though it's not a rational number. You can manipulate it along with the rational numbers. Okay? Okay. So, how do I go about dividing two such numbers? If I want to get it if I take two of these numbers, a plus b root 2 and c plus d root 2, I want to divide one by the other and put it back into this form, this standard form. Yeah.
You can multiply by the reciprocal, c minus d root 2.
Yeah, exactly. You what we call this rationalizing, right? If you think back to algebra 2 in high school, this is how you get rid of radicals in the denominator, right? You multiply by the negative of the radical, or in this case, since we have a term that has no root 2 and a term that has root 2, you just multiply by the sign flipped on the factor that has a root 2. Yeah, good. So that is to say, written out, we want to put this in the standard form. We'll just multiply by 1 in a fancy way. This is just a factor of 1, so the expression remains, it's the same quantity, but it will allow us to clear the denominator of radicals. Okay, so what does this give us? Well, in the numerator, we just use the formula for multiplication we developed just now, right? So we get AC minus 2BD plus BC minus AD times root 2.
Bless you.
And in the denominator, we just get C squared minus 2D squared. Sorry, D squared. Okay, so now I just split the sum across the denominator, and to get it in precisely this form. Okay, so all together, this gives me is AC minus 2BD divided by C squared minus 2D squared plus BC minus AD root, well, let me put that to the side. C squared minus 2D squared times root 2. And then here we are, two rational numbers. Yeah. Okay, good. So we can do this same procedure, this same formal procedure for every real number. okay? And that allows us to, well, once we do that, if we do this formal adding in of every real number, we end up with just the real numbers. That's a subtle result to prove, but take my word for it. And we are able to solve many, many more polynomial equations in this number system that we arrive at by adding in all real numbers. But there are still many equations that we cannot solve when we arrive at this number system in which we added in all real numbers. Okay? So let's record this. Similarly, adding in all real numbers, we can solve many more polynomials. But not all polynomials. Here's a simple example. X squared plus 1 is equal to 0. Has no solutions in the real numbers, right? Because of the properties of the square root function, right? Square root function is not defined for negative input. However, even though there is no real number that corresponds to the square root of -1, we can do this formal procedure that we did with root 2 to the rational numbers. We take our modified set of numbers that we obtained by formally adding in each of the real numbers, and now we arrive at some symbol which cannot be represented by a real number. But we can do that formal procedure just the same to this new symbol. Okay, so, there is no real solution to this. I kind of wave my hands at that, but here's something I want to make this thematic throughout the course. We will side by side make algebraic and geometric developments. Right? Every statement I make that we prove together, I will, as often as possible, try to make an analogous geometric remark. We can start that now, right? What's the graph of this polynomial?
Parabola above.
It's a parabola with y-intercept 1. Right? If it had a solution, it would cross the x-axis somewhere. This just gives you some idea of the scope of what we're missing with only considering the real numbers. How many polynomials don't intersect the x-axis? Most of them, in some sense, in some correct sense of most, right? So we're missing a lot, even by adjoining uncountably many things to the rational numbers. kind of depressing, but we're on the right track though. Okay? There's no real solution to this, but we can carry out our formal adding in procedure. With some new symbol for a solution to x squared plus 1 equal to 0. So, definition. Let's choose a symbol. I. Which we'll define to be this concept which a priori makes no sense. Then a complex number is an expression of the form a plus bi, where a and b are real numbers. Of course, I bet we're all familiar with this too, right? The Blackboard Bold R, just the collection of all real numbers. Good. So let me just add that two complex numbers are equal if and only if two complex numbers, I should specify what they are. A plus bi and c plus di are equal if and only if A equals C and B equals D. Okay, this might seem somewhat pedantic, but we're defining a new notion of number. We should be precise about what equality means. Okay. Right. So I'd just like to point out that many if not most, I'll say, many if not most branches of mathematics have some roots, somehow stem from trying to solve some sort of equation. This is why I chose this view of the historical development, because yet again, here we have like, oh, how do we guarantee that we have solutions to polynomials? That's what we're trying to do. Add in enough additional symbols to guarantee that we can solve polynomials in our resulting number system. Yes?
Is the set of complex numbers enough to solve every polynomial?
Yes. Which is the amazing thing, right? By looking at just this simple quadratic polynomial and adjoining a symbol that represents a solution to that, suddenly we get every polynomial becomes solvable in the resulting system of numbers, the complex numbers. Somewhat miraculous fact, right? Because when we adjoin the real numbers, as I said, we're adjoining an uncountable number of numbers. And still, we're very far from being able to solve most polynomials. Yet by just throwing in this I, we can solve everything. Okay? We're going to prove that in a couple weeks. Or maybe even less than a couple weeks, but we'll get there. We'll get there. But yeah, great question. I was going to say that later. Thank you. Okay, so let's get back to our development. So we define our arithmetic operations in this set of complex numbers just the same as we did for when we threw in root 2. It's completely analogous, right? So let's just write it down anyway. A plus bi plus c plus di is equal to a plus c plus b plus d I. A plus bi times c plus di. Well, we just, again, multiply the binomials, and we get AC minus BD as our supposed A, and we get BC plus AD times I. Okay? And just as before, A plus BI divided by C plus DI. Well, we do the same thing as when we rationalize the denominator, when we had a number of the form A plus B root 2 with a irrational. We just flip the sign of the part with the I in the denominator, right? So I guess this is worth writing out just to see one other time. Okay, so I commit arithmetic here, and I get AC plus BD divided by C squared plus D squared plus BC minus AD divided by C squared plus D squared times I. Okay. Right. So again, this is just what we've seen before. Formally the same. Of course, using the fact that I squared is -1. Okay, so let's see. Here's another definition. The real part of a complex number is the real number A. Okay, so I'm defining this function RE that takes in a complex number and spits out the part of the complex number which does not have a factor of I. Okay? And the imaginary part is, again, I'll define this function im of A plus bi, which just spits out the real coefficient on I. Okay? Yeah. So, these are functions of a complex variable that we will take some time studying over the course of the next week. And we will try to, we'll see how far we can take the development of calculus with these functions in particular, in addition to many others, but these will be of some interest to us. In fact, they're they're a part of a set of essential counterexamples of what complex functions behave nicely enough to do calculus on. Okay, that's an intentionally vague statement, but I hope it gives you some preview or intuition of what's going to happen. Okay, so let's also say that if A is equal to 0, the complex number is said to be purely imaginary. Now, sometimes people ask, why is the terminology surrounding the foundations of complex analysis so fanciful? Why is it, why are these numbers purely imaginary, those that are not containing a real part? Oh, that's because in the Victorian era, there was a lot of pushback to this process of formally adding in something that was not representable as a real number. In fact, the lore goes that Lewis Carroll wrote Through the Looking Glass as sort of a protest, as a lampooning of the intellectual pursuit of complex analysis. It was viewed as absurd or meaningless that one should consider adding in something which had not previously been considered a number. So, weird historical genesis of this terminology, but we're stuck with it now, I guess. Okay. Anyway. We often use the letter Z to represent a complex number. And as such, we may write that Z is equal to the real part of Z plus I times the imaginary part of Z. It's kind of a notational thing here. Oh, I should write lower on that part of the board, huh? Okay. Right. So, we also denote a set of all complex numbers by blackboard bold C. Right, so again, I feel fairly confident that you know this, but I'm going to ask anyway. We're comfortable with this set builder notation, right? This is the form that the elements take. A bar meaning such that any additional specifications we want to make on the formation we made on the left. Okay, good. Right, so blackboard bold C, it's obvious, right? C for complex. Same thing R for reals. Why are the rational numbers called Q? This is just a fun side note. Any guesses? Quotients, yeah, good. Thank you. So you've probably also seen blackboard bold Z for the integers, right? Anybody have any guesses on that one?
The German word for numbers, like Sauger.
Yeah, it's something like that. I don't know German that well, but it's the German word for whole. Yeah. So, again, mathematics is littered with weird historical things that we just held on to for no particular reason other than they were popular at one point. I just think that's interesting. Okay. So, here's a fact that I'm going to ask you to prove on the first homework assignment. There is no order relation on the complex numbers. That is to say, it's complete nonsense for me to say 3 plus 2i is less than 1 plus 7i. There's no notion of less than in the complex numbers. A stark contrast to any of the number systems that we used leading up to constructing the complex numbers, right? Integers, rationals, real numbers, everything in between the rationals and the real numbers when we formally adjoined root 2. Those those all have order relations. It makes sense to say when something is less than or greater than another thing. We depart from that here in C, which is somehow connected to this fact that we discussed briefly a second ago, that we are able to solve all the polynomials. So this is start thinking about this, because it's going to be a homework question, and I'll guide you through a little easier, but see what you can come up with before I tell you anything. Okay, right. So let's talk about how we might geometrically represent the complex numbers. number?
Two real numbers.
Two real numbers. So, we might guess at a geometric interpretation of how to represent complex numbers. I mean, how do we typically think of two real numbers at the same time? Yeah, an ordered pair, which fit very nicely into a plane. You know? So, since two real numbers determine a complex number, it's natural to use the plane, the plane R2 to represent complex numbers. Right, so just exactly what you would expect. Right? Just some example points. Let's say here we have the complex number 2 plus 3i. Let's just take here 1 plus I. And why don't we just say down here is minus 3 minus 4i. Exactly what you would expect. No surprises here. But there is an opportunity to add some terminology to our scheme. In this setting, we call call the x-axis the real axis, and the y-axis the imaginary axis. Okay. And we call this the complex plane. As opposed to R2, recall that we usually call this the Cartesian plane. What's the difference between R2 and C? They look exactly the same, right? Is there a difference? Is this an equality? Yes.
They have different domains.
What do you mean by domain?
There are more numbers that can be put on the complex plane that can be put on the Cartesian plane.
That's not exactly what I was looking for. there's exactly one complex number for each pair of real numbers, and vice versa. So they're kind of equinumerous, right? So not exactly that. Any other thoughts on this?
I mean, R2 is constructed out of two real numbers, C is constructed out of real imaginary part.
That's true, that's true. If I give you two elements of R2, what does this mean? A comma B times C comma D. How do we multiply two ordered pairs?
I guess, like what people can do is you can define that dot as a dot product. Consider that.
True, you could take the dot product of these two elements of R2, viewing them as vectors, but that gives you an element of R, not an element of R2. There is no a priori multiplication defined on elements of R2. Whereas, we wrote a formula for how to multiply two complex numbers together. Okay? So that's the difference. There's multiplicative structure on the complex plane. And we'll see what that means geometrically as we advance. So topologically, R2 and C are homeomorphic. You don't have to know what that means. It means they're topologically equivalent. But algebraically, the difference lies in the multiplicative structure. Okay? Good. So yeah, let me answer this question. What does this mean? Nothing. Unless you make some definition. So, side note, in case you're interested in algebra, you can ask about the ways in which you can add, throw in a multiplicative structure onto R2. And in fact, you can classify the number of distinct ways to do that. That's way out of our purview, but there are interesting questions to ask here, just in case you're interested. Okay, anyway, you gotta keep me on track here, sometimes I get way off the mark. Right, now let's go back to complex numbers. Here's a definition. So, the absolute value or modulus of a complex z equal to a plus bi is defined by this our typical absolute value sign that we remember from real numbers, but the formula is quite different. The square root of a squared plus b squared. Okay, so where does this formula come from?
Pythagorean theorem.
Yeah, the Pythagorean theorem. Right. Let's let's look back at our point representation, right? I come out 2, and I go up 3. What the modulus is telling us is the distance from this point representation, in this case of the complex number 2 plus 3i, to the origin. And since these are our coordinates, essentially, of where our number lies in the plane, we can apply the Pythagorean theorem and just take the square root of the sum of the squares of our components. Yeah. Okay. Okay, so what's the modulus of 0? 0, yeah. What's the modulus of I divided by 2? 1/2, yeah. Okay, somebody compute the modulus of 3 minus 4i. Is 5, yeah. Let's make the computation on the board. Or you might recognize this as a 3, 4, 5 right triangle. Okay, good. So, just from the definition. I have the definition. The modulus of any complex number is a non-negative real number. And furthermore, the modulus of some complex number z is equal to 0 if and only if z itself is the 0 complex number. Okay, so I mean, these facts are fairly transparent when you take the geometric viewpoint, right? No other point in the plane has distance 0 from the origin, right? And furthermore, distance is always non-negative, unless you're at the same point. Yeah. Okay. So let's suppose we have two complex numbers, z1 given by a1 plus b1i, and z2 given by a2 plus b2i. Then let's compute the modulus of z1 minus z2. Well, let's first compute the difference. So z1 minus z2 is the same as a1 minus a2 plus b1 minus b2i. And now we just apply the definition of modulus, and we get the square root of a1 minus a2 squared plus b1 minus b2 squared. This hopefully is a familiar formula, right? Especially when we consider the point representation of complex numbers. What is this quantity telling us? Yes?
The distance between 2 points.
Yeah, exactly. This is the distance between the points that represent z1 and z2 in the complex plane. The distance between the points representing z1 and z2 and z2 in the complex plane. Okay. So basically all we've done here is recast some old favorite formulas from geometry of R2 in the language of the complex machinery that we're building. Okay? Now, here's where things might get a little more interesting. We can use this formula to describe certain curves in the complex plane. Okay? So, namely, let me, for example, let's fix some complex number, b naught, and some real number, we'll call it r. Then the following expression, or rather I should say, the complex numbers v, which satisfy the modulus of z minus z naught equal to 0, equal to r, define a curve in the complex plane. Who can describe this curve? Yes?
A circle with radius r centered at 0.
Exactly. Yeah. We're looking at, let's unpack that slightly. We're looking at the set of complex numbers z, which are a fixed distance away from our fixed number z naught. Looking at all the complex numbers which are exactly r away from z naught. Okay? In this case, a circle. Let's say here's z naught. I'm really not much of an artist. I apologize. This is not even close to a circle, but let's pretend it is. Okay, this is an R, and I should be a little better about that. How's that? Okay. Okay. So, let me ask you. Let me pose you a question. I'm gonna give you some equation involving a pair of moduli and ask you to describe the curve that this cuts out in the complex plane. Okay, so. Okay, so let me ask you to describe, by which I mean describe geometrically, the set of complex numbers satisfying the following equation. The modulus of z plus 2 is equal to the modulus of z minus 1. Okay, so let's take, let's see here. Let's take 3 minutes. Think about this, and then we'll discuss it together. And, really enjoy the fact that we're in person. Feel free to discuss this with your classmates. I'll be right back. So how do we feel? Any thoughts about how to address this? Yes.
I have no idea if this is right, but I took the modulus with z equaling square root of a squared plus b squared, but included 2 plus a squared plus b squared.
Okay.
Then set that equal to the opposite side, and then did a minus 1 squared plus b squared. And then set that equal, and I got an equation, but I can't remember what shape it is.
Okay, yeah, I mean, that's definitely on the right track. That's like, if you want to proceed algebraically, that's 100% the correct steps to take in the beginning. You're right. And we'll pursue that.
Yeah.
But before we do that, I just want to say, if you think just geometrically, you might come up with an answer without doing hardly any computation at all. What we're looking for is the set of complex numbers z, which have the same distance from the complex number negative 2, and the distance from the complex number 1, right? Remember, the modulus of a difference is the distance between 2 points in the point representation. Okay, so let me record this. And of course, I'm emphasizing the geometry because it's simultaneously less intuitive for most people, including myself, but it actually requires less work, less computation. Okay, so let's just note. So we're looking for complex numbers z, which have the same distance from -2 and 1. So let me draw a picture. Here's -2. Here's 1. Yes?
So would it just be a vertical line at -1/2 in the real axis, and
Yeah, exactly. Right? So we know one point in the plane, i.e. complex number, that has the same distance between it and -2 and 1. That would be -1/2. Has the same distance to both -2 and 1. Right? And in fact, everything that lies along this line also has the same distance. Let me pick some other point on this line, right? These two legs of this triangle are the same length. And so it will be for any point on this line. Yeah? So this is again back to the theme that I mentioned at the beginning of class today. We'll try to do things algebraically and geometrically whenever we can. Okay, so now let's take the suggestion and proceed algebraically and verify that we get exactly this equation. Okay, so algebraically, let's say z, the modulus of z plus 2, what I used x's and y's here, is the same as the modulus of x plus iy plus 2, or in other words, x plus 2 plus iy. And just now we can apply the definition of modulus, right? We get the square root of x plus 2 squared plus y squared. Okay, now let's quickly look at the right-hand side of the equation. The modulus of z minus 1 is equal to the modulus of x minus 1 plus I times y, which by the definition of modulus is equal to the square root of x minus 1 squared plus y squared. Okay, so now we'll just equate those two expressions. What did I say here? Square root of x plus 2 squared plus y squared is equal to the square root of x minus 1 squared plus y squared. Well, I can square both sides, right? So x plus 2 squared plus y squared is x minus 1 squared plus y squared. Well, subtract y squared from both sides, right? Now I'll just FOIL this out. X squared plus 4x plus 4 is equal to x squared minus 2x plus 1. X squareds cancel. So what do I get in result? I add 2x to both sides and subtract 4 from both sides. Divide by 6 and simplify. We get the equation of a vertical line. So it's a subtle art, a skill that you will develop over time to decide whether it's easier to think about a problem geometrically or algebraically. Here, it wasn't too bad either way, right? Proceeding algebraically is slightly longer. That doesn't really matter. Both are completely valid. We will see situations where one view is much harder than the other. And you will often be able to arrive at an answer in either viewpoint, but you may inflict more pain upon yourself if you don't choose the right path. Which is okay. There's nothing wrong with that. It's a choice, though. Okay, let's do another such example where I'll give you some equation and we'll try to puzzle out what curve it makes. So let's ask which complex Z satisfy the modulus of Z minus 1 is equal to the real part of Z plus 1. Let's just talk about this together from the outset. Who has any guess or intuition of which pathway is easiest here? The algebraic or the geometric? Yes.
The geometry.
Okay, why do you tell me why you feel that way?
Doing algebra with specifically the real part of the Z and having the full Z on the other side in the modulus seems difficult. It seems more difficult than just looking at how it changes geometrically.
Okay. Does anybody agree or have a differing viewpoint on this?
I would disagree.
Okay,
I would say algebraically it seems easier.
and why is that?
Because you're good. It's only two variables, and it seems like the most complicated expression we'll have is a radical, the square root of the modulus.
A single radical. Okay. So here's what I think. It's not very obvious what this function, real part of Z, looks like in the complex plane. I anticipate that we'll get to a point where we can say something about it, but it's really not that easy to think about geometrically in this case. So I would say when you're dealing with some function that has a real or imaginary function, the real part or the imaginary part, it's usually best to proceed algebraic. And this is good. I'm glad that we have this discussion because this is how we'll develop our sense. Did you have a question or a comment?
Oh, I think I know what it is, but
Okay, yeah.
never mind. Well, it looks just like a circle, because real Z is a number that plus 1, so modulus equals radius.
That's great. That's good intuition. That you're looking at how powers and fractional powers interact here, right? And you're like, oh, well, a circle usually has a square root or squares in it, right? So you're close. It does resolve into a conic section, but it happens to not be a circle in this case. So let's do some algebra together and see what happens. Yeah. Okay. So oh, sorry, I forgot a question mark there. Right. So we already computed in our last example what the modulus of z minus 1 is in terms of letting z be equal to x plus iy, right? So let me just reiterate. The square root of x minus 1 squared plus y squared. And the real part of z plus 1 is just equal to, well, the real part of z is just x, right? So we get x plus 1. And we set these equal. Okay. Now we're squarely in the domain of doing algebra with real variables, right? Okay, so I'll square both sides to get x minus 1 squared plus y squared is equal to x plus 1 squared. FOIL everything out, x squared minus 2x plus 1 is equal to, oh, sorry, plus y squared is equal to x squared plus 2x plus 1. Okay, so my x squareds cancel, my 1's cancel. So I can then conclude that I get y squared is equal to 4x. Yes?
So wouldn't that be the set of all complex numbers such that a plus 2 root a I?
I'm sorry, what's a in this?
Okay, sorry, x.
X.
Yeah.
So, yeah, so I'm sorry, say what you were saying.
I said, like, if you solve that for y, you would get, so 2 root x equals y. And then
Yeah.
your complex number is in the form x plus yi. So any complex number of the form z equals x plus root 2 x I should satisfy that?
Yeah, that's right. Yeah, good. But now, so yeah, that's right. You can certainly write down a formula. Z is of the form something in terms of x plus something in terms of x, right? What is this geometrically though? It's a parabola on it's a parabola which is not a function, right? So the problem with including square roots is that you have to say positive and negative, right? So since we're just trying to specify the complex numbers which satisfy this equation that we started with, it's better to leave y squared here, right? So yeah, this is just a parabola that opens kind of wide, right? It's dilated by 4. Okay. But yeah, so that the answer that you gave with square roots in the expression for the complex number is a partial answer. Those are all satisfying, but you have to take the negative, the square roots as well. Yes.
So if we were like formally given this question, can we give an answer that's either algebraic or geometric, or it should be like?
Yes, unless it's specified in the question.
Okay.
Yeah. And I'll try to be clear about that if I'm looking for a particular thing. If I don't say, then anything is acceptable. Okay? Good. Good. Okay, so we're pretty on track. I have a little bit of time. And there's essentially one more, yes, I'm sorry.
Just a quick question. Is there any type of orientation to that curve?
No. If you mean orientation in the sense of differential geometry,
Yeah.
no. There's no orientation a priori. Yeah. It admits an orientation, but we're not considering that. Yeah. Right, and this is actually, you're touching on what becomes like algebraic geometry. Just kind of like the study of surfaces that are defined by polynomials rather than manifolds, which are defined by smooth functions or analytic functions. We'll start to talk about that by the end of the term, but for now, no orientation assumed. Okay, so as I was saying, there's one more kind of fundamental operation that we'll use in making calculations with complex numbers. And we have just enough time to introduce it and talk about some of the basic properties before we adjourn for the weekend. So here's the definition. The complex conjugate of a complex number z equals to a plus bi is the complex number z bar equal to a minus vi. Okay, so really just give a name to this thing that we use to commit division, right? Then the reason we do that is because we end up using this a lot. There are a lot of formulae that we can derive involving this construction. Of course, what does this mean geometrically? Well, it just means that we're reflecting about the x-axis, right? Here's z equal to a plus bi. If I flip the sign on b, I just go to the other side of the x-axis, right? Okay. So, how much time do we actually have left? Oh, a little bit still. Good. So, note that z is equal to z bar if and only if the imaginary part of z is equal to 0. Right? If you take the interpretation that conjugation reflects about the x-axis, the only things fixed by reflection about the x-axis are the points which lie on the x-axis. Right? If I reflect this point about the x-axis, it does nothing. Right? And these are exactly the points where the imaginary part of z is 0. Okay? Okay. I guess I should say that is, z was in fact a real number. Okay. All right. So the first thing we'll do on Tuesday is discuss the 8 properties that conjugation possesses. some identities involving conjugation. Okay, so have a great weekend, and I'll see you Tuesday.